Hello, everyone, and welcome to the 39th Surface Ventures webinar. It'd be great if you could say hi in the chat and tell us where you're joining from today. So we've already got Ben, who I said hello to, of course, and Stephen. Great to see you there. My name is Dr. Sam McMaster. I'm the content manager for Surface Ventures, and we are a non-for-profit organization, and our mission is to provide world-class surface and materials science engineering education for academia and industry. Today, it is my pleasure to introduce Professor Ashley Martini from the University of California, Merced. Ashley Martini is professor and chair of the Department of Mechanical Engineering at the University of California, Merced. She has been working in the field of tribology for the past 20 years, with research reported in over 200 published papers. She's also recently published a textbook titled Introduction to Tribology for Engineers. Her contributions to research, as well as teaching and service to the profession, have been recognized by multiple prestigious awards. Many thanks as well to today's partner, Artec Instruments. We will have a short presentation from Philip Kemp later in the event. We'll be releasing poll questions and handouts from Artec Instruments throughout the event. I will highlight these when they are released in the chat. As we go along, please do type your questions into the chat, and they will be marked for the Q&A session, which we will have after both talks. We're planning to go for around 60 minutes in total today, and we'll be sharing a link for your attendance certificates later in the event. So let's welcome our speaker to the stage now and proceed with the event. Okay. Hello, Ashley. Good to see you.
Hi, everyone.
Let me just bring your slides up. Fantastic. There you go. Take it away.
All right. Hello, everyone. It's my pleasure to be here today to talk to you about MOS2 lubricants and their role in the new space economy. Before I get started, I'd like to acknowledge that the results from my group that I'll be sharing with you today were collected by current and former students at the University of California, Merced. And I'd also like to thank Surface Ventures for the opportunity to present to you. So today's seminar is going to be organized as follows. We'll start at a real high level and talk about tribology in the new space economy. Then we'll dive in and focus on molybdenum disulphide, or MOS2, in space tribology and its properties in space conditions. Then I'll share some recent results from my group in terms of benchtop characterization and understanding fundamental mechanisms. So let's start again with tribology in the new space economy. What does this term mean? The new space economy refers to the rapid growth of this industry in terms of economics. So this figure on the right is showing annual revenue of the space industry growing over time rapidly and projected into the next few years. The projection for growth of this industry is such that it's supposed to reach $1 trillion by 2024, which is really not that far away. The growth of the industry is attributable to a variety of different factors, but three of the biggest ones are: first, privatization of the space industry. So again, referring to the figure on the right, if you look at the orange and blue bars, these represent the commercial or private sectors, and you can see that they do represent the most of the growth of this industry. Expansion has also occurred due to rising demand for space data or satellite connectivity. And also, perhaps of most interest to this audience, growth has occurred due to advances in technology. Another way to look at the growth of the space industry is in terms of number of objects sent to space. So the plot that you can see here on the left is number of objects sent to space per year starting in 1990. And you can see that it's pretty constant, around maybe 100 or so objects sent to space until about 10 years ago. And then there's a rapid increase in number of objects sent to space, such that now we're talking about thousands of objects sent to space per year, or multiple objects sent to space per day. This has completely changed the way we think about the space industry, and in fact, probably the way we think about the Earth itself. So how does tribology fit into this big picture? Well, spacecraft, anything that goes to space that involves moving mechanical systems requires lubrication, and therefore involves tribology. There are a variety of prototypical mechanical components in space systems: solar array drives, reaction wheels, tracking antennas. All of these are mechanical systems that do have counterparts here on Earth, and we often think about space mechanisms in the context of, again, their terrestrial components. Just as an example, the figure on the right shows required life versus sliding speed for a few prototypical space components where the lubrication regime is identified, sort of in the context of the traditional Strybeck curve. So there are many similarities between space tribological systems and terrestrial tribological systems. But there are also many key differences and, in fact, challenges associated with tribology in space. I would categorize these broadly into extreme conditions and, more recently, design for reusability. So, as many of us know, the conditions in outer space are completely different from those that we have here on Earth, and therefore mechanical components must survive those types of conditions. Depending on the mission, this could include vacuum, could include radiation, very hot, very cold, or sometimes multiple different conditions in the same mission. This is an extreme challenge for tribological systems, but it's also an opportunity for us as tribologists because it gives us access to a wider range of conditions through which we can potentially better understand tribological mechanisms. The other big factor is, again, more recent and associated with that more rapid or more frequent number of objects launched into space, and this is design for reusability. Today's launch vehicles are planned or intended to be used for multiple missions, where they go up to space, must experience space conditions, come back to Earth, experience some of our more challenging conditions like coast and marine environments, and then go back up. So these types of components have to survive many orders of magnitude longer than ever before. Again, a significant challenge, but also an opportunity for us as designers and engineers because it provides an opportunity for more frequent iteration and potentially more rapid design and development. All right, so I've talked a little bit at a very high level about tribology. Now let's focus in on today's topic, which is molybdenum disulphide. Molybdenum disulphide, or MOS2, is a naturally occurring element. It can be, again, found in nature or synthesized in the lab in a variety of different crystallographic phases. All of these phases comprise molybdenum and sulfur layers, and they can be found present in different crystallographic phases, having different thermal, mechanical, and even electrical properties. However, from a tribological perspective, the most important aspect of molybdenum disulfide, or MOS2, is this layered structure, where we have very strong bonds within layers and very weak bonds between them. What this enables is the layers to slide very easily relative to one another, such that the material has low shear strength and imparts for us low friction and wear and good tribological properties. MOS2 in lubrication is nothing new. In fact, the patent for MOS2 as a lubricant additive is almost 100 years old now. So it's been around for a while. And in fact, one can purchase MOS2 additized lubricating oils and greases for specialty products online even today. However, there are significant challenges with wet lubrication for space applications. The biggest one is associated with missions that have to experience extreme cold. Just as an example, our Earth's moon at night or in permanently shadowed regions can reach minus 200 degrees Celsius. There's also great interest in exploring faraway lands like Jupiter's moon Europa, which has an icy crust and the potential for water and life underneath. But again, this requires actuation in extreme cold. To use a wet lubricant in this scenario, you basically have to heat it. This requires significant weight, significant cost, and most importantly, takes a significant amount of the total energy available for the mission. Another challenge with wet lubrication is the finite vapor pressure of liquids. This could lead to outgassing or oil loss and contamination of very sensitive instruments. Therefore, for many missions, wet lubrication strategies are just not an option. The alternative, and what we're going to be talking about the rest of today, is dry film lubricants. These are slippery solids or solid lubricants and widely referred to in the industry as DFLs. MOS2 dry film lubricants are already used. Again, these are coatings or solid lubricants that are used without liquids. A couple examples are shown here. On the left, you see photos from the James Webb Space Telescope and an MOS2 coated bearing. On the right, you see the more recent Mars 2020 rover, where the sample caching system, the actuating components in the sample caching system relied upon MOS2-based dry film lubricants. However, there are significant challenges. So for the mechanical engineers out there, this is maybe bring you back a little bit, but mechanical systems and components have been designed for decades, for a long time, to operate and are optimized for liquid lubrication. Just as a couple examples, I've shown you here some images from the ubiquitous Shigley's machine design. On the left side, you see a worm gear where the efficiency of the component is related to the friction coefficient. And on the right side, you see a rolling element bearing where we see the load-life relationship. These tribological metrics, friction coefficient and life, are pretty well characterized for liquid lubricants, and mechanical systems are designed to operate with these parameters. However, there's really a lack of information about what these parameters are for MOS2 DFLs, and even if the fundamental design equations may or may not be applicable. So how does MOS2 operate as a dry film lubricant in space conditions, and what are these design metrics? First, how do we measure that? So ideally, one might wish to measure performance metrics in the application, for example, in the International Space Station. This may not be accessible to any of us, so often testing is performed here on Earth. This can be done at the component or subsystem level, or most commonly using benchtop tribo tests, where simple geometries like a ball and a flat are used to provide a comprehensive set of characterization data. Again, I'm referring to things like friction coefficient and life for MOS2. But I think I mentioned this before, that conditions are extreme in space. So when we perform testing here on Earth, we do want to try to mimic space conditions. And this can mean a lot of different things. First of all, it's important to test in ambient conditions. It's important to test in air. And this is because every space component before it's sent to space has to be stored and tested here on Earth. And it's expected there was unplanned relative motion in components during transport to launch sites. We'd like to perform testing here on Earth in a vacuum-controlled environment to mimic the low oxygen and low humidity conditions of space, as well as the low pressure directly. Or an alternative, easier approach is to test in dry nitrogen, where test chambers are flooded with nitrogen. Again, the goal to remove the oxygen and humidity to kind of mimic the space condition in a just a little bit easier to access type approach. We've already talked about temperature. It can be very hot, it can be very cold, and these types of conditions can be mimicked in specialized chambers here in a terrestrial environment. So what do you get out of this? Shown on the right here is an artist's rendition of a friction coefficient versus sliding cycles plot. You measure lateral force, you calculate friction coefficient, and it looks something like this. You see a rapid decrease right at the beginning of the test. This is associated with run-in. Then you see a long, steady state, low friction period. This is the majority of the operation of the mechanical system. And then at some point, the friction again increases rapidly. This is associated with loss of the dry film lubricant in the wear track and is referred to as the wear life of the coating. Wear life is often more important than friction in space applications, because once the wear life is done, the component is also done. Therefore, the life of the lubricant can determine the life of the coating. So let's look at some representative results. What I'm showing you here are two plots of the friction coefficient as a function of either cycles or time from the literature. On the left, I'll bring your attention to comparing the green line and the purple line. The green line was tested at room temperature in humid air, and the purple line at room temperature in dry nitrogen. And what you can see right away is that the performance is far better with the purple data set, where we have no oxygen and humidity. And when I say better, I mean lower friction coefficient and longer wear life. In the figure on the right, the tests were performed all at 40% humidity, but at different temperatures above room temperature. And this result shows you that friction decreases with increasing temperature, again, above room temperature. So there's clearly a sensitivity to the environment of the MOS2 dry film lubricants. This can be largely attributed to the interactions between the MOS2 and oxygen and or water, both of which can disrupt the easy shearability in different ways, although. Oxygen can chemically bond with the molybdenum disulphide to ultimately form MOO3, a less lubricious counterpart. Water physically adsorbs to the MOS2, particularly at defects and edge sites. Both of these are disruptive and therefore can explain the observed poorer performance in humid conditions. However, oxygen and water interactions can also explain some temperature dependence. The figure on the right is showing you friction coefficient versus temperature. The red data set was performed in water environment, and the light blue squares was performed in oxygen. And you can see that the red data set decreases with increasing temperature, and this is because increasing temperature desorbs water, whereas the blue data set increases with temperature, and this is because increasing temperature accelerates the chemical reactions associated with oxygen MOS2. So the key of understanding some of these trends is understanding the role of water and oxygen in interacting with the MOS2. So how do we mitigate this? One approach to mitigating the adverse effects of the environment and more generally improving the performance of MOS2 dry foam lubricants is through the use of what are called dopants. These are elements or other compounds that are introduced into the MOS2 during deposition or synthesis. There have been a variety of different elements explored for space DFLs, including titanium, nickel, gold, and antimony oxide. These elements or compounds can either substitute for the MO or S in the lattice, they can intercalate between the layers, or they can potentially form separate phases. And which one of these happens depends on what is the element, what is its concentration, and the conditions during synthesis or deposition. Shown here are a few more representative results, in this case for doped MOS2. On the left, I'll draw your attention to the top black and blue lines. The black line represents pure MOS2, and the blue line represents antimony oxide gold doped MOS2. And right away, you can see that the blue line runs much, much longer than the black one, indicating longer wear life. On the right plot, we're looking at wear volume as a function of load. The black data is the pure MOS2, and the blue and red are the gold or titanium doped MOS2, and we can see lower wear with the introduction of the dopants. So this type of data is incredibly valuable because, kind of going back to our goal, we want to know these performance metrics, things like friction coefficient and wear life. We need this information to utilize MOS2 in design of mechanical systems. However, there's quite a bit more to be done. And in the next section, I'm going to share some recent results from our lab. So let me start with the study that we performed to compare nickel-doped and undoped MOS2. Nickel has been a dopant for a while and is maybe a little bit more of a historical perspective, but has been considered as a space dopant for a bit. We performed these tests in ambient conditions, again, trying to mimic the testing that occurs before launch. And what I'm showing you here are SEM images of the surfaces prior to testing, where you can see in a scratch on the surface the lamellar or layered structure of the MOS2. Here we see a representative result. Again, this is friction coefficient versus sliding cycles. We see that prototypical or expected decrease at the beginning of the test. Long, steady state constant friction coefficient followed by a spike that corresponds to wear life. We performed an elemental analysis such that we confirmed that indeed that spike at the end, that high friction spike, corresponds to removal of the MOS2 from the wear track and therefore the life of the coating. But the key observation from this figure on the top of the slide is that the wear life of the nickel dope coating in the light blue is much longer in this condition than that of the pure MOS2. However, we repeated this same test at different conditions, different operating conditions. Specifically, we performed the test at different pressure and speed conditions designed to mimic those that would be expected in a corresponding gearbox for a space application. The results are shown here on the right, where you're looking at wear life as a function of pressure, where again, the speed is also varying. And the main take home here is that at low pressures and high speeds, indeed the nickel is beneficial and helps extend the wear life. Whereas at high pressures and low speeds, we see really no benefit from using the dopant in these cases. Next, we extended this study to include another dopant, in this case, an antimony oxide gold, which is a little bit more of the state of the art these days for MOS2 dopants. And we also explored other conditions. So we moved on from air at room temperature to dry nitrogen at room temperature to dry nitrogen at 0 degrees Celsius. Shown here are some representative results from these tests, and I'm not going to spend a lot of time on this slide because we'll go into it in a moment. But what you're looking at on the left is the pure MOS2, the middle is the nickel, and the right is the antimony oxide gold. The darkest colors, maybe not the brightest colors, represent the air, and you can see right away that those tests failed soonest, probably as expected. And also, if you're perceptive and you're looking at the x-axis, you can see that the rightmost plot, the x-axis is much, much longer, already giving us hints that the antimony oxide gold doped coating is lasting much, much longer than the other two. Shown here is the complete data set. This is the wear life of these coatings at the 3 different conditions and the 3 different coatings. A lot to unpack here, but we can draw your attention to just a few points. First of all, the wear life, which are the solid bars, is shorter in air for any of the dopants. In addition, the antimony oxide gold wear life is much longer than that of the other 2 in any of the conditions. The 2 red arrows on the far right indicate that the test was stopped before the wear life was reached. And lastly, looking at the temperature of the test, the temperature results for the test that did fail, these are the square hashed bars, we can see that for the pure MOS2 and the nickel-doped MOS2, the wear life is shorter in the colder condition. So let's talk about now even colder. So looking at our best case coating, the antimony oxide gold coating in dry nitrogen, tests were performed at -60 and -120. So even colder. What I'm showing you here is number of cycles versus temperature, where the solid symbols indicate the wear life was reached, and the hollow symbols indicate the test was stopped prior to reaching the wear life. The left figure is for a lower pressure condition, the right figure for a couple higher pressure conditions. But the main upshot of these plots is that as we go from room temperature to -60 to -120, the wear life of these coatings decreases. Again, this type of information, this data is invaluable as we try to take MOS2 as a dry film lubricant to an enabling technology for space. However, what we really also want to do is understand the mechanisms. Why do we see these trends, and can we develop ultimately predictive tools? That's what I'll be discussing in the last section of this presentation. All right, so let's come back first to that nickel study that I talked to you about. So you may recall that in some conditions, the nickel-doped MOS2 lasted a bit longer than the pure MOS2. To try to understand this, we analyzed the run-in phase, the first hundreds of cycles. We started by analyzing the depth of the wear track using optical interferometry. In the plot on the right, I'm showing you the depth of the wear track normalized by the coating thickness, such that 1 means that the depth of the wear track has reached the bottom of the coating. And what you can see on this plot, which only goes to the first 250 cycles, is that even within those first couple hundred cycles, we've already reached, in some cases, the very bottom of the coating. This is contradictory. This appears to be contradictory with the many thousands of cycles that we found for wear life based on friction. We also performed some microscopy of the early cycle results and found some differences in morphology between the nickel-doped and the undoped coating. So this suggests that this material or debris generated in the first few sliding cycles may be incredibly important as we think about why the wear life might be longer for the nickel. So taken together, this kind of disrupts the simple mechanism that I started presenting you with, right? We talked about a long wear life followed by failure when the coating was gone. The results I've shown you here, along with multiple others in the literature, support a slightly more complex mechanism, where during these initial stages of sliding, and perhaps throughout sliding, debris or flakes are generated. And these are helpful. They're lubricious debris or flakes that are available in the contact and ultimately are responsible for enabling the long wear life and determine the length of the wear life of each coating. So this is a pretty interesting idea, and it also enables us to try to move in a little bit closer to understand some mechanisms. In fact, it could point us to a way to understand the cold temperature results. Recall that we saw that wear life was shorter in cold temperatures. What I'm showing you here on the right is a plot from the literature that shows the distribution of MOS2 debris size as a function of temperature. The white distribution is the coldest temperature at minus 100 degrees Celsius, and these are the smallest particles. So these results together suggest that possibly this useful lubricious debris is smaller when it's cold, which could possibly contribute to the shorter wear life. The other advantage of this idea of the flakes or the debris is that we can zoom in a little bit closer and focus on nanoscale mechanisms. So we take our tribal system and we zoom in just to the debris, just to the contact. So MOS2 has been shown to be a triangular shape, has been shown to be prototypical or expected in equilibrium conditions, as shown in the microscope image here. And this idea has been leveraged in previous simulation studies to model the MOS2 in the atomistic scale. We followed a similar approach in our work, and for those who care, we developed atomistic models using the ReactFF potential as implemented in lamps. The first thing we did was try to understand why the debris might be smaller when it's cold. To do this, we performed simulations of simple tension on MOS2 sheets, as shown in the lower left. And just a quick note that looking at the stress distribution in the sheet, we already do see this triangular patterns. But perhaps more importantly, in the stress strain plot on the right, you can see that as we go from room temperature to colder, the fracture stress increases. Higher fracture stress is associated with more elastic energy stored in the material, and therefore more energy dissipated upon fracture, and theoretically smaller flakes or debris. We then evaluated the potential effect of this flake size on this water, on water absorption. So we're talking about cold and we're focusing on water as opposed to oxygen. We performed simulations of water interacting with these triangular MOS2 flakes of different sizes. The figure on the right shows you adsorbed water density as a function of flake size for two different flake stoichiometries. And the key point here is that as we go from larger flakes to smaller flakes, the adsorbed water density goes up, meaning the impact of the water is more significant or perhaps more severe for smaller flakes, and therefore could more adversely affect the performance of the DFL. However, it's possible there's no water at all. To evaluate this, we performed simulations as shown in the lower left, where we took these MOS2 debris or flakes and we sheared them. Shown on the right is a plot of shear stress as a function of time. The red data set is the largest triangle or flake, the triangular shaped flake, and the black and the blue are these smaller flakes. And what you can see is that with or without oxygen, the shear stress is much higher, or they're less lubricious for the smaller flakes. While this isn't directly a measure of wear life, it does suggest they are indeed less lubricious. So lastly, inspired by previous research which has shown that the orientation of MOS2 lamella with respect to the basal plane and with respect to sliding is critical to its performance, we evaluated the orientation of our flakes. This is shown graphically here on the right, where the color indicates the alignment of the flake. So yellow means the flakes are not oriented well with the sliding direction, and purple means they are oriented quite well. And already you can see just visually, the small flakes are less aligned, which should correspond to less good performance as a tribological system. So cold temperatures, smaller flakes potentially explains the reason we see the shorter wear life in those cold temperature experiments. All right, so we've gone pretty deep. Let's come back up for air to conclude the presentation. I'll summarize by saying I hope I have convinced you that MOS2 is a key enabling technology for this rapidly growing space industry and economy. There's already space components with MOS2 lubricants, but design challenges remain associated with the fact that there's just not enough data for these tribological performance metrics, and we really don't quite have enough understanding. This can be achieved, again, through benchtop test characterization and also surface microscopy and simulation-based approaches. So the challenge, coming back to the beginning, is that there's just not enough information about these typical tribological design parameters for MOS2 dry film lubricants. I suggest that we need a combination of characterization and understanding to meet this challenge. Characterization, I believe, should focus on commercially available DFLs because, again, things are being sent to space right now as I'm speaking, but also DFLs for which we know the composition so that we can interpret results. We want to try to mimic space conditions as closely as possible here in our terrestrial environment and try to make apples to apples comparisons between DFLs, between conditions, and so on. This should be coupled by efforts to understand mechanisms. We should design simulations to complement experiments. And even when a head-to-head direct comparison is not possible, we should corroborate trends so that we can give some confidence to the simulation results, and also make comparisons between micro and nanoscale features that we can observe in microscopy. So finally, what are the Martini keys to success? I believe that we really need close collaboration between applications engineers who are, again, sending things to space right now, and research scientists who have the laboratory tools and the expertise to understand mechanisms. Together, they can have impact. We also need to bring both experimental and computational tools across length and timescales to the fore. Together, these are what we will need to gain on the understanding towards predictive tools. I would also suggest that we should focus on open access publications so that we can share information broadly and potentially even data sharing. For example, some journals have article types like data notes. But maybe most broadly, we as an engineering and scientific community can make an effort to get the word out, to make sure there's widespread understanding of the critical role of tribology and MOS2 in space technology. Together, we as a scientific community can have a huge impact on technology that's going to determine or maybe even enable the future of space exploration. So finally, I'd again like to thank you for your time and attention. I can take some questions now, or also my email is here up on the slide, and you're more than welcome to email me anytime. Thank you again.
Thanks, Ashley. That was a fantastic talk. So I think with questions, what we'll do is we'll have Philip's talk now, and then we can do a combined Q&A session. So answer questions 5 so far waiting for you, and yeah, then we'll answer them all together. Okay, thanks. Okay, so now we'll have a presentation from Philip Kemp from Artec Instruments. Let me bring your slides up, Philip. Excuse me one moment. There you go. Take it away.
Yeah, thank you. Thank you very much for the invitation to this Surface webinar and to the Surface Venture event in combination with Ashley Martini and the very nice presentation about MOS2 lubricant for space application. So I will introduce shortly Artec Instrument if you are not familiar, and I will give you some application of the turbometer that could be related to the space application as well. So Artec Instrument is a scientific instrument manufacturer for surface characterization, and there are in fact different applications related to this technology. So we are developing and manufacturing advanced mechanical and surface testing equipment that implies turbometer, but not only turbometer. There are in fact other instruments and technique like 3D profilometer that makes it ideal instrument, in fact, for surface characterization in different method of testing or different environment. So Artec Instrument, in fact, the headquarters and the manufacturing of instruments are based in San Jose, California, in the USA. But there are in fact offices throughout the world. I'm based, in fact, in Switzerland for the European and Middle East office. But there are also offices in China, Japan, India, Singapore. And we have, in fact, a large number of distributors worldwide, including a range of 20-25 distributors that could be close to you. And if you have any question, we would be happy to get in close contact with you regarding the different applications in tribology or mechanical surface testing. In fact, tribology is covering a large range of our applications, but we are not following only the application with tribology. So the multifunction tribometer that I will explain you today is measuring the coefficient of friction and wear of material, and that's a very nice continuation of the presentation of Ashley Martini. But there are, in fact, for characterization of material, other interests. We have the scratch and indentation tester for the characterization of hardness and adhesion of coatings. The fretting tester, which is a very specific tribology range of measurements which is generally at high frequency and very low amplitude of oscillation. And it could be combined with measurements on the 3D deformation, plastic deformation, wear of material, and the 3D profilometer are in fact bringing a lot of information for surface characterization. What I will insist today is about the vacuum material tester that is also able to do friction and wear measurements under vacuum condition. And from the presentation of today about the space economy and space application, it's in fact very interesting to do tribological measurements in a vacuum environment. There have been, in fact, in the recent development of Arctic instruments, other instrumentation in tribology, rolling sliding, twin roller, three roller tester, air jet erosion tester, but also specific turbometer related to lubricant testing. The mini traction machine SRV tester or four ball tester are testing technique or method that are well known in the lubricant industry. In fact, one of the interests of the multifunction turbometer are the possibility on a modular platform to be able to do different range of measurements. So it's not necessarily an instrument that is able to do all kind of testing in all conditions with one configuration, but the possibility to add different module of measurements in order to go from very low force of measurements in the milliturbometer range, in the range of millinewton, to the very high load for specific application, up to 10,000 Newton. And as well from very low speed to different high speed testing with different kind of motor. And the modularity is also brought by the different module or function of functional modules that we could install on the instrument. So we can do rotary motion, linear reciprocating, block on ring, disc on disc, and other different mode of testing that I'm not explaining today. But in fact, environmental control is a key factor for tribology testing. You have seen that results of coefficient of friction and wear could be highly dependent on the environmental condition, meaning that if you test a certain material in air or in vacuum or in different level of humidity, you could have very different results, not only on the coefficient of friction, but also on the wear lifetime of this kind of material. And I will insist today a little bit about this range of application. The interest of the multifunction turbometer as well and the specificity of Arctic instrument is the possibility to have mechanical testing in front of an instrument, like on the MFT 5000 turbometer, where you have the turbometer set up in front of the machine, but with the X and Y motorized stage, you are able to install a 3D profilometer at the back of the instrument in order to automatize and automatically make measurements between tribology measurements and 3D profilometry in an integrated manner on this kind of instrument. So the big advantage in the modularity is the fact that we could be closer to the real condition of the tribological test. If you have bearing, we have more condition of testing, which is in a rotation mode. But if we have other kind of material, the linear oscillation could be more appropriate to reproduce the condition. With many conditions, we are also testing lubricant, with the lubricant presence, we could do testing in a liquid cell and simulate the condition in the presence of liquid lubricant. But as well for both of these conditions, in dry condition or in liquid condition, we are able to do testing in heating and cooling condition. And that's in fact one of the key factors that could be for the space industry as well, is the possibility to do testing in different environments. You could do testing in a vacuum condition with a vacuum turbometer, but on a multifunction turbometer, you could also do testing at different temperature and different level of humidity. So one of the very popular setup with our kind of instrument is the possibility to do high temperature testing. So depending on the application and the level of budget, it's in fact possible to propose a heating stage that is going from a low range of heating to the middle range or high range of heating in order to fit the different application. But it's true that there are many requests nowadays with the possibility to do cooling as well. because if you want to reproduce the real condition in different countries, it is true that you need to create an environment which is doing cooling and heating as well, and that's what we try to propose on different kind of instrument. So one of the interesting option is in fact the low temperature chamber. It's basically a closed chamber, not as close as a vacuum system, but a relatively closed system where you can, with the circulation of a water cooling system or a liquid cooling system, being able to control the environment and the low temperature. It is true that depending on the liquid which is used, in the case of liquid nitrogen, you can go to very low temperature, minus 120 degrees Celsius, but it's also possible to use other kind of liquid in order to go to minus 40 or minus 60 degrees Celsius. The other evolution that we had was the possibility to offer a new humidifying system or humidifier in order to have in a closed chamber the possibility to control the level of humidity. And it's true that people may forget that in tribology, the coefficient of friction may vary very strongly with the level of humidity, meaning that if you test in a different country, you may have different results if you may forget to record the level of humidity in the laboratory. But with this kind of option, we can control the level of humidity and in fact reproduce different level of humidity in order to see the variation of the coefficient of function for friction as a function of humidity. And then, of course, for space application and other application as well, the vacuum turbometer could be quite interesting. There are different coatings and lubricants that are very well known to have a very large difference of coefficient of friction depending on the level of vacuum. MOS2 was presented today, but there is also the DLC coating, which are very well known to have a tremendous variation of coefficient of friction if it's tested in air or in vacuum. And then it could be combined with different level of temperature control in order to reproduce the real condition in the field. The interest of the vacuum system is the fact that we can have a force control where we could change the speed of rotation, we can change the load applied in order to be able to change the condition of testing without changing or without cutting the vacuum, meaning that you can change the condition of testing while doing the tribological test. In fact, why are we able to do very stable measurements and very precise measurements in vacuum? It has been relatively easy for Arctic Instrument by the fact that we have developed a patented system called argon sensor, which is based on capacitive sensor. And capacitive sensor are in fact not sensitive to vacuum system or humidity level, in fact. And then we could do testing with a very high stability and negligible drift over a long time. So I will just like to introduce a little bit the different technology of Arctic Instrument. We have been using piezo sensor for high frequency tests like fretting tester. But the advantage of the capacitive load cell patented by Arctic Instrument is bringing a very high level of stability. We have a very specific system with elastic arm, which is based on two force sensor measuring the lateral force measurements during the test. And the fact that you have two sensors is making a high stability measurements and a high precision measurements. And this is really a high technology and high precision measurements that we can explain you more in detail if you are interested, but that really bringing a lot of stability measurements, meaning that we can do measurements with this capacitive sensor over a 48 hours time. And we are in fact showing a very high stability and no thermal drift with this kind of instrumentation. So to just conclude on this kind of measurements is that I explain you shortly that we have a 3D profilometer combined to the tribology measurements, and that makes it very useful for characterization of wear on the material. You can imagine stopping the tribological test at different cycle or different level in order to make a 3D image on the surface, and then bringing a little bit insight or more advanced vision about how much is the level of plastic deformation and wear on the material while you are doing tribological testing. In fact, the big interest of this combination and the typical friction analysis that we may do with our instrument is in fact to record the coefficient of friction as a function of cycle or time, and see on a specific example on a coating to see where the coating might be breaking, what would be the wear time of this material, and then with the 3D profilometer being able to observe the 3D deformation on a very precise level on different locations on the sample. So that really this combination of 3D profilometry with tribology is bringing a lot of advantage for characterization in tribology. Just to conclude, I presented you shortly the multifunction tribometer MFT 5000. It brings it with a high level of modularity, a lot of function. I only introduced a few of them today. The focus was more on the environmental control because that's a nice explanation about the interest of changing the environment with different material, and the explanation of the previous presentation was showing that by changing temperature, humidity, or vacuum level, you could really observe a very big difference in the coefficient of friction and wear of material. And this combination is in fact very important for tribology measurements. And I'll thank you for your attention, and I will give then the lead to Sam. Thank you very much for your attention.
Thank you very much, Philip. Great presentation on a very capable piece of equipment and lots of options, which I'm sure people will like. I think we do have a question asking about that as well, which we'll get to in a moment. So for now, let's begin the Q&A session in a moment. I'll just invite Ashley back on stage. But for right now, what I will do is release the link to the attendance certificate. So that is now available for you all in the bottom left. That attendance certificate will be available for the next day. So please go ahead and click on that now, but come right back. We'll be doing the questions. Okie dokie. So we will begin with, we'll go from first question asked and sort of proceed like that. So we have our first question from Steve, who asks, how does the TI doped MOS2, which is commercially available, compared to the SP203 gold doped film at cryogenic temperatures in vacuum or in dry nitrogen?
I don't know. One of the challenges of this, I guess, this whole field is that it's difficult to make head-to-head comparisons. I'm trying to think if there's a specific paper that made the comparison you described there, but often conditions are not the same from test to test. And by conditions, I mean all sorts of things. I showed you that pressure and speed matter. So pressure and speeds being different, substrate materials being different. The deposition, the way these coatings are deposited has a huge, I didn't talk about it at all, but it has a huge effect on the results. So I guess the short answer is I'm not sure. I'm trying to think if there's a paper that did a head-to-head comparison that you described, but if not, I would have a hard time answering it because there's so many differences between tests that it's hard to infer these types of comparisons. Sorry.
Sometimes it's just better to say I don't know. It's extremely complicated. On just one quick question for me on deposition of these coatings, would it normally be a PVD system, physical vapor deposition, or are there others that are typically used as well?
Yes, you can use the PVD, but there's more. This is a whole nother presentation.
Yeah.
Because I'm talking about deposition, and a lot of the research and scientific community is focusing on a sputter deposited coatings. But in practice, a lot of the coatings are not done that way because it's not fast and it's not cheap. So, just sort of conceptually, you can paint on coatings, right? And this is a cheaper approach. There are many cheaper and faster and less geometry sensitive approaches to applying coatings that are probably used more often in practice. Although The research is often done on the sputter deposited coatings. So yes, but that doesn't really capture the breadth of the challenge associated with how these are applied to the component.
Absolutely. No, it's just a lot of my sort of previous work was on PVD coating, so it's always a thing I like to ask and sort of find out more about for different coating types. Okay, let's move on to the next question from Paula, who asks, would tungsten disulphide work as a good substitute for molybdenum disulphide?
Yes, there's quite a bit of work on tungsten disulphide. Instead of a molybdenum disulphide, I'd say the amount of research for MOS2 is much, much larger than the amount of research done for WS2. But they've both been shown to be very good. There are a few head-to-head comparisons. MOS2 remains much more popular, both commercially and in research. And I think some of that is historical. Some of that is, the industry. Originally, tungsten was more expensive than molybdenum. I think there were a couple studies that showed MOS2 outperforming WS2 in some situations that kind of veered people away, but certainly it could be used. There's research towards it, just not enough compared to the MOS2 that I would be able to say definitively which is better, because again, it's an it depends answer.
Okay, thank you. I have a question from Will, who asks, well, that's actually partly been covered. Why do you think there's a focus on MOS2 compared to WS2 for solid lubricant or space applications?
I think there's a few different reasons, but none of them are it's definitively better. There's the cost piece. I think when they were, and I may be talking a little bit out of turn here, but I think when they were looked at as lubricant additives, that MOS2 was better in terms of like staying in solution than the WS2 early on. MOS2 was looked at earlier, so that might be part of it, but I wouldn't be able to say definitively it's always better.
Okay. Thank you. Another question from Steve, who asks, was the small flakes research only done with nitrogen-doped MOS2? Are there any reasons to expect different mechanisms with differently doped MOS2?
Right. There's two questions there, and probably I skimmed over this part, but the small flake stuff we did was actually without nickel doping. So the first thing that I talked to you about the mechanism of generating flakes, that was from the nickel-doped MOS2 study. But then we took that idea and we applied it to the cold temperature study, and that was in the experimental work we were talking about antimony oxide gold, and in the simulation work we were talking about pure MOS2. And the reason for the pure MOS2 focus was mostly a simulation limitation. But perhaps the more important part of this question is, are the mechanisms going to be different? And the answer is probably yes. This idea of doping MOS2 it's super interesting. I mean, I showed you a couple examples here where adding dopants to MOS2, I mean, order of magnitude improvements are possible. But why that happens is really poorly understood. There are hypotheses. There's some beautiful work showing microscopy that, where does the dopant go? How does it perform? What does it do? But there's really no, I guess we'll say, smoking gun mechanism for what dopants do. And I think it depends on what the dopant is, its concentration, and again, how it's introduced into the coating. So I guess the short answer is I don't think anything that I would say about one dopant or an undoped case can be just ported over to another example, but there's lots of interesting research to be done in this area. So super important and interesting question that I can't answer.
That's good, thank you. A little comment from Steve there I've noticed in the chat, who says, if I remember correctly, tungsten disulphide is better at elevated temperatures, but it's probably in the literature. Yeah, I think that's... It
could be, I don't recall. It could well be. And probably you could find a study that shows whatever you want if you seek hard enough.
Yeah,
this does resonate what you said here, Steve. So you're likely right.
Yeah. I think, probably our best recommendation is to do a bit of a literature search and see. There's a lot out there.
That's right.
I have a question from Eric, who says, great talk. I wonder if the flakes are sensitive to gravity. Do you think friction would be worse in 0G or upside down terrestrial orientation? It's quite interesting.
I have never thought of that question, Eric. I don't know. I suppose most of these systems are quite enclosed. So it's not in the application. It's not a flat surface where tribometer where the flakes could. If you flip the whole tribometer upside down, the flakes could fall out. I suppose that most mechanical systems in space applications are enclosed. So this may or may not matter. I guess I don't know. You're right. They're slippery. So what would hold them down, right? I don't know. Interesting question. We'll see. We'll see if Philippe, can you design an upside down tribometer? We just rotate the whole thing.
Yeah, might be possible, but
okay, there you go.
Yeah.
But 0G would be more difficult.
Yeah, that would be quite a feat. We could, yes. Okay, got a couple of questions from Haley here. First one of which, for you, Ashley, what did you use to test shear?
I'm not sure what this question is referring to. In the experimental work, it was literally Philippe's tribometer was used to measure lateral force. Stress can be obtained by using the Hertz contact equations for Hertz point contact. In the simulations, we have a flat surfaces. So we're measuring the force on the topmost flat surface and dividing by the cross-sectional area to give us shear stress. Hopefully that answers the question.
Yeah, I think so. And one for you, Philippe. How much does the vacuum tribometer cost?
And the upside down vacuum tribometer.
And the upside down one as well.
Yeah, no, what is true is the fact that you have a vacuum chamber increase the budget quite significantly. So that means a lot of people would be interested to have a vacuum turbometer and not able to find it necessarily the budget. But in fact, the interest has been shown that you can get great measurements and results for a very important application. And I was surprised by the fact that the space industry economy is growing so fast. And that's the reason why we get more and more requests. And I think you cannot get away from the fact that if you have new lubricant, new coatings, you may need to test them under vacuum if they are going under vacuum, because what I has shown is that nitrogen can replace some part of measurements, can bring some information. But at the end, you would need to validate some materials and some testing. And the vacuum turbometer has a big advantage. But it's true that compared to a normal turbometer, you can double or triple the cost depending on the configuration. There is nevertheless a primary vacuum, secondary vacuum, different kind of testing with heating, without temperature control. So that's why our span of budget is really wide. So I would invite you just to a little bit specify with a contact person from Artec Instrument or a distributor, just what kind of interest do you have, and then we would give you a quotation that would be easier.
Okay. I'll pass on contact information when I sort of look through everything after the webinar. So
it's also interesting, sorry, just to interrupt you, but in this kind of vacuum system, we're also able to do scratch testing, which is used, in fact, for a lot of coating application to test the adhesion of coatings, the shear stress that you can have on material. MOS2 are relatively soft materials, so you don't see necessarily a delamination like you see on a PVD coatings. But you could have this combination of scratch testing, tribological testing on a lot of material, including MOS2, that could also bring insight about material characterization.
Okay. Thanks, Philippe. So we have, just looking at this, we have 6 questions marked remaining. We're just at the hour now. So if it's okay, we'll run a little bit over. We'll clear up these questions. Is that okay with the both of you?
Yeah, that's fine.
Okay, great. Another question from Eric. He says, thank you, Philip. We have an MV2 vacuum tribometer in our lab, and it's great. However, I would like to add a specific sensor to the inside of the chamber. Can you provide vacuum cable feed-throughs to pass a few more wires into the chamber?
Yeah, that was part, in fact, of my explanation before. The vacuum turbometer can be a little bit manufactured according to different geometry. So we can have more or less feed-through with this kind of system. So if there is already 1 or 2 more feed-through available, then it's possible to add certain option on the machine, additional sensor or additional cable for different sensor. after we will contact you directly just to answer your specific need. But it's true that the vacuum system is not only one model, we have different versions of it. Yeah.
Okay. Thanks, Philippe. Just a quick comment there on a question from Steve, who asks, will the slides be available? We don't share the slides, however, the recording will be available, so you will be able to see what was presented. Okay, so that will be sent to you automatically, and then it will also be available later on the Surface Ventures website. Okay, let's move on to the next question. From Nauduru, apologies if I mispronounced that. They ask, are there any specific reasons for using MOS2 for space-related applications over other similar 2D materials?
So by similar materials, I guess I'm going to not talk about WS2 because that is indeed considered for space applications. But if by similar materials we're talking about carbon-based materials like graphite, I can answer that one. And it's really having to do with the sensitivity to the environment. So as I showed you, MOS2 performs poorly when oxygen and water are present, but it performs really, really well in dry nitrogen and vacuum, and that is the space condition. On the other side of the coin, graphitic materials perform really well in more humid environments and poorly in the absence of that. And that's because in the case of the graphitic materials, it's a layered structure also, but you need the terminating hydrogen at the edges of the layers so that they don't bond to each other like this. So that kind of explains the graphite versus MOS2 thing, if that was your question.
I like that answers it very well. Thanks. Okay, so we have another question from, apologies, that appears to be a Polish name, so I'm going to skip pronouncing that one, just in case I do a terrible job. But they ask, how do you obtain high enough adhesion of MOS2 coatings?
I guess that depends on what is meant by high enough, but adhesion is really important. It depends on the substrate material. It depends on the roughness of the substrate. So there are studies that show that the roughness of the substrate itself affects the performance of the coating on top of the substrate. So that's related in there. And it again comes back to what we were talking about earlier. It depends how you apply the coating. So I don't know, it depends on what high enough means, but the dials you have to turn are substrate material, how the coating is applied, if there's a binder or something like that, and then the roughness of the substrate. Okay, thanks. I had one of the questions I haven't marked, but since you mentioned roughness, it might be a good idea just to bring this up as a comment. Does doping impact the surface roughness of an MOS2 coating? I don't know. I don't think so. So I did mention these are in relatively low weight percents, and what I'm talking about here is on the order of like 5 to 10 weight percent for these elements or compounds. I don't think I know the answer to that question. My instinct is to say probably not, and it may not matter that much because as soon as I'm assuming you're talking about the roughness of the top of the coating. As soon as you start sliding, that morphology completely changes. So whatever was inherently rough on the top of the coating changes as soon as you start sliding. So I don't know. If I had to put money on it, I'd say no, but I also don't think it matters too much.
Yeah, I feel like investigating that will probably take quite a bit of time and probably quite a sensitive either interferometer or AFM type of setup in order to really investigate that. Yeah. Okay, so next question from Zhudong. I hope I pronounced that correctly. It says, thanks for the exciting presentation. Can you talk about the application prospects of MOS2 in atmospheric and high temperature environments? Is there a better solution besides the doping technology?
Is there a better solution? Well, there are a lot of challenges for MOS2 in atmospheric conditions. It's kind of inherent to the mechanism of this easy sliding. This is impeded by oxygen. It's impeded by water. When oxygen and water are both present, they combine. There are a lot of challenges for MOS2 in atmospheric conditions, and that's why it's usually not the go-to coating for these types of applications. High temperature is usually not the Achilles heel of MOS2. Depending on, well, let me say that a different way. It depends how high you go. We talked about the fact that as you increase temperature, increasing temperature has opposite effects on water versus oxygen. So increasing temperature accelerates chemical reactions between oxygen and MOS2, whereas increasing temperature desorbs water from the MOS2. So as you increase temperature, the effective water goes up and the effective oxygen goes up and the effective water goes down. So it depends probably what you mean by high temperature. This, again, dopants can help, sometimes not. I would say do another solution. Yeah, off the top of my head, I'm not coming with anything right now, but if I think of anything, I'll pass it along to you. Thanks for the question. I'm running out of steam at this point.
Okay, I think I hope some of these ones are some of the final ones are a little easier. Final one from Haley, I believe, who asks, can you speak anything to the wear mechanism of TI MOS or titanium doped MOS or chromium doped MOS?
I don't think I know about the mechanisms, and I don't think anyone really does. There are a few papers that do head-to-head comparisons of these two dopants that you mentioned, just a few out there in the literature, so you can see some performance evaluation at specific conditions and some mechanisms suggested here and there. But I think that I don't personally know a definitive mechanism for those, and I'm not sure that others do either at this stage. That's why it's a really interesting research topic.
Absolutely. Question from Ibon, who says, very interesting talk. Is there any MOS2 already approved, or sorry, doped MOS2, excuse me, approved for applications in space?
So approved, I guess, approved is probably the important part of this question, because with the privatization of the industry, what does that mean, right? When it was governments always sending things to space, then the idea of approved materials and approved dopants was a pretty big one. But with privatization, a lot of that stuff just went right out the window. And I'm not saying that's a bad thing. In fact, in many ways, it's a really good thing. So if you're asking if they're using doped MOS2, I would say yes, I think so. Approved, maybe not as relevant anymore in today's space world. Space economy, space industry.
And now onto our final question from Ahmed, who says, an out-of-topic question, but if time allows, what do you think about the super lubricity efforts nowadays, and is there a possibility for some space applications at certain conditions with MOS2? So I think any super lubricity potential with MOS2.
Probably. I guess I'm not really that close to the latest literature on super lubricity. I know that a lot of the efforts are focused on scaling up. So early super lubricity was found at nanoscale, and there's a lot of efforts to make nanoscale super lubricity possible at macro scales. However, that's not really my focus area, and so I'm not up with the latest literature. I anticipate that, for space applications, some of the technologies we develop for terrestrially here for super lubricity could be used up there as well, and hopefully it will include MOS2. It's a good suggestion.
What is true is that we are doing some testing for super lubricity, and it's generally very low friction coefficient. We're talking about 0.01, so extremely low. And MOS2 might be slightly higher, but then indeed the application was to apply a different higher load on a bigger sample, and it was really the goal of doing scaling with super lubricity.
Right.
And that's a big goal in the automotive industry, which is working quite a lot on super lubricity with DLC coatings. It might be a little bit different focus on space application, therefore.
Okay. So I think with that, we've come to the end of our questions. So thank you both very much for answering
Thank
those.
you for the very interesting question. And thank you for the very nice organization.
Yes.
Not a problem.
Thank you, Sam.
Not a problem at all. Thank you to everyone in the audience for attending and for your great questions. I think it was a very interesting Q&A session. Thanks to Artec generally for supporting this webinar. We wouldn't be able to do what we do without our partners. As a reminder, you can visit surfaceventures.org. You can find our previous talks, recordings thereof, and soon we'll be updating the website with our keynote for May. I do have the registration link for that available now. That will be on our website later. But if you're interested in this now, please click on that as a featured action. Additionally, you'll be able to find information for that in our, on our website, of course. Emails and LinkedIn. We have our fortnightly newsletter, Modern Surface, and the next issue releasing tomorrow morning, UK time. So if you're interested for that, please go ahead and sign up. And finally, we would just like to say, please do take the time to advertise this to friends, colleagues, anyone who you think would be interested. It's always great that we get new attendees and more people that are interested in material science, surface engineering, tribology to come along. So with that, I'd like to say thank you all very much. Have a great rest of your day, and we'll hopefully see you all in the next event.
Thank you very much.
Thank you, everyone. Take care.
Thanks. Bye-bye.